So let's get started. So we're talking about artificial neural networks, ANNs, and we're moving toward deep neural networks, what's most typically called deep learning these days. And we need to cover this method, and remember, this is a method for us of analysis. I do talk about the theory behind deep neural networks in the machine learning class, which I'll teach again next year. But if you want, in the meantime, you can watch it in YouTube, right? In the same channel that you have this course, if you're interested. There's a lot of material, theoretical material, that you have to go through before you can actually get to the theory of deep neural networks. But here we're describing it as a method because the method that we're going to use in all three steps of vision: low level, mid level, and high level vision, right? So first thing, we're going to apply to low level vision. And for that, we have to understand how these networks work. And remember that we had this input vector x, and then we had a vector here z, and an output vector y, z being the hidden vector, the hidden layer, right? And x and y, the input and the output respectively, right? So that if it were linear, aj, right, would be the sum of xi multiplied by the weights, right, which are the weights that are associated to each of these edges of the graph, of this directed acyclic graph, the aj. And then we add an offset, right? And we can add an offset, we said, by adding an additional node of that graph, right? That we can add, say here, we call it x0, which is connected to each of these nodes here. And similarly, you can add the z0, right? That is connected, node that is connected to these ones, right? And that serves as the offset. And why do we do that? Because this is the definition of a hyperplane, right? And remember that we already know how to solve this system of equations. That's exactly linear least squares, right? Linear least squares are the equations of finding that hyperplane. Now, what we do is we make this nonlinear by then adding some additional function g, right, where g is some nonlinear function. So far, so good. And we've discussed that one of the functions that was used for quite some time was the sigmoidal function, right? The logistic sigmoidal that we already discussed last time. And as we will see, that function is actually very important, right? Which function we use here as a nonlinearity for these neural networks is actually going to make a huge difference in our algorithm. Okay. The other thing that's going to make a big difference is the number of hidden layers, right? Remember, these are called the hidden layers because this is the input layer, the output layer, which are observable. These are the unobservable hidden layers, and we can put as many layers as we want, right? And when you have multiple layers, then we're talking about the deep neural network. Okay, because there's a deep number of functions. Now, importantly, remember that all of this process is nothing else than doing f of x, right, equals y, where f is the whole function defined by this daj, right? Makes sense? But you could also interpret this as there is a first functional mapping here, f1 of x, that gives you z, and then f2 of x, and so on, up to the last one, fl, whatever, or capital L, let's use for the number of layers of z. So if we call this z1, z2, and so on, there'll be z of l minus 1, right? Oops, I said equal. This is f of, right? And then this f corresponds to the composition of f1, f2, and so on, right? Actually, I put this in the wrong place here. FL. Right? Okay. So far, so good? Any questions? Okay. So then we started talking about how we're going to do network training, right? So by network training, what we mean is that we now want to define or identify the values of these parameters, the Wij's that I don't have. I don't know what these values are. I need to change these values, right? These are unknowns to me. I want to change these values such that f of x is actually equal to y, or is as close to y as possible, right? Do we know of a criterion that measures that? It's not a tricky question. What's that? Well, what do you mean? Yeah, no, that's not exactly it. You're almost there. The what's that? Least squares, right? The least squares criterion. So why don't we write this down? Let's write down the least squares criterion. Whoops. Okay. So let's write down the least squares criterion. So our, over here, the least squares criterion is the error for our W vector, whatever W vector we currently have, of 1/2 the sum of, say, n1 to capital N, the number of samples of y. I used f there. You may want to use f or y here. F of xn given the parameters w minus the targets. Actually, let me change that because I'm using this notation here. So let me change this output to targets. And then these functions, I'm just going to call them y1, y2 to yl, OK? OK. So these functions, let's call them y, because that's what I did last time. I want to make sure that they follow the same notation. Tn. And then what am I missing here in least squares? A square, right? I'm going to use the 2 norm. Now here, the set of these xn's, right? And again, from 1 to capital N, it's a set of samples that I'm given, right? These are observations that I have. And the corresponding Tn's are the targets that I have, right? And the pair, so the set of, actually, let me do it as a vector, maybe, of xn, Tn as a pair, right? And from 1 to capital N is called the training set. The samples are the training set. And it's called the training set because we're going to use these samples and the corresponding target to find the solution, right? Using, for example, the least squares error function. OK. So the problem here is how to now find the value for these W's. OK? So let's see how we can do that. So how do we determine W, our parameters and or unknowns? So first off, let's write down here the, I'm going to write the conditional probability of the target variables. Okay, let's do that. So the conditional probability of the target variables is given by the probability of the target T given condition on the set of samples X, capital X. So I'm going to call capital X this set here, right? So this is equal to capital X. Actually, let me use probably this new font so that it's clear. I'm going to do it like this. Okay. And given the parameters, W, right? And what's this equal to? Well, for each of the samples, right, this is going to be, not that I'm leaving a space here, this is going to be the probability of Tn given Xn and the parameters, right? And then I have this for every single sample, right? So what is the, the conditional probability is the product of all of these, right? And there'll be n from 1 to capital N, right? And now here, capital X, right? It's going to be a matrix or maybe a tensor. In general, it's going to be a tensor, right, of the samples that I have. OK. Now, assuming, and that's an assumption I'm making, that T is normally distributed, that means, so i.e., the probability of T given X and W is equal to some normal distribution of T given my function y of X, W, and some variance. Okay, so let's say that the variance is the inverse of beta. Okay, 1 over beta. And now to solve this equation, what I'm going to do is I'm going to take the log of this function, right? So I get the log likelihood, and I'm going to add the negative sign. So that's called the negative log likelihood. So the negative log is, let's see, it's going to be the sum of y, right? The sum, because I'm going from products, I compute the log, so that's going to give me the sum, right? The sum of these y xn's w minus tn's, right? Squared minus, I'm going to have, this is going to be beta over 2, right? Because it was 1/2 before, wasn't it? I added this 1/2. So this is going to be times beta times that 1/2, beta over 2. And then I'm going to have the log of beta times n over 2 plus n over 2, the log of 2 pi. Okay. Okay, so from here, I could find the maximum log likelihood solution, right? I could just find the solution for this if that function were convex, right? And the function would be convex if this function were linear, right? Fortunately, this function is nonlinear, and that will typically lead to non-convex functions, right? Log likelihoods, which means that we have to find a mechanism to define a solution. And for this, we're going to use a method that's called gradient descent. Okay. And we're going to be using this method constantly throughout the course. So the idea of gradient descent is that if I have a function e that I'm trying to minimize, that maybe looks something like this, okay? This is whatever function that I'm trying to minimize or maximize. In my case, I want to minimize this. Then if I have a current solution, right, for some w's that I have here, I have a current solution that it's here, and I want to get to the closest minimum that I can find in that function. The way to do that is to follow the direction of the gradient, right? Okay. Now it's called gradient descent because I'm descending toward the minimum. And there's the other version, which is called gradient ascent when you're looking for maximums. Okay? For maxima, you're ascending. For minima, you are descending. So to find this, I want to compute the gradient of whatever function I'm trying to minimize or maximize. Okay? And then, as we know, equal that gradient to 0, right? Because 0 is where our solution is. Or we want to get as close to 0 as we can. So our goal is to minimize our function e of w. And we wish, if we could, to have a gradient for w that's equal to 0. Because that's at the minima and at the maxima, the gradient is going to be 0, right? Because there's no directionality. That's what we did, the same thing for linear least squares, right? And we solved linear least squares in 5460. And, well, actually here as well, right? We reviewed it. OK, so to do that, what we're going to do, we're going to take this current value. Let's call this, I don't know, w at time k, right? And what I'm going to do, I'm going to take this w at time k, and I'm going to add to it some increment of w at time k and make this w at time k plus 1. Okay? So that I'm going from this point to another point, maybe here, right? Which is going to be this wk plus that increment of w, right? And then once I'm here, this is going to be w at k plus 1, and we're going to add another increment and then another increment until I reach the minimum, right? I'm going to do this iteratively. Make sense? OK. Now this increment of w is a function of the gradient, right? So a function of the gradient of EW. So for example, a classical example for this function. So I'm going to say EG. For example, I could write that WK plus 1 is equal to WK plus, or minus rather, because I'm going down, that's descent. The function is actually going to be that gradient multiplied by a constant. Okay? So nu, is that nu? Never remember the Greek letters. Eta? Is that eta? Okay, so eta. Eta, the gradient of the function, right? E of w. Right? And that would be the gradient of w, and that w obviously is at time k, right? Because that's going to keep changing. Now, eta here, this parameter, right, eta has to be larger than 0, right? Because otherwise I'll be ascending. And if it's 0, I will not move, right? This is called the learning or training rate. Okay? And it's called the learning rate because the higher it is, the faster I learn. And the smaller it is, the slower I learn, right? And It's tricky. I'm not going to discuss very often here how to define that value. Again, in machine learning, I spend a lot of time in these details. But if you have an eta that's too big, what's going to happen? You're going to overshoot, right? You're going to go over the minimum, and you're going to go to some other value on the other side, right? And if it's too small, then you're never going to converge to the minimum, right? So you have to find a balance for that parameter. OK. So this is the maximum likelihood solution that we have derived here. So in order to find the solution, or having found a solution, rather, let's say, with this method, right? So the method, again, you take your criterion, you compute the derivative of that criterion, you iterate, right? And you find a W that gives you a gradient equal to 0 or a very small number, right? OK? And once you have determined this, then let's call this solution. We'll call it WML for maximum likelihood. How about that? OK? Because we're trying to maximize the likelihood function. And then given that, we can now feed that solution into this equation and solve for beta, right? And that way, I can get the solution, which is 1 over beta ML. I'm going to use again because it's going to give me the maximum likelihood solution of 1 over n, the sum of n from 1 to capital N of y xn WML minus Tn squared, right? And that's it. That's just the direct solution for my other parameter. OK? So there are many ways of using gradient descent. And I want to summarize them very quickly here because the differences are actually important to understand the different methods that we'll review throughout the course. So the first one, and probably most famous one, is stochastic gradient descent. Again, if you're finding the maxima, then it's ascent. Otherwise, exactly the same. So in the approach that we just described, you could use all the training samples at the same time to define the probability or the W, right? And if you do that, that's called the batch algorithm because you use the whole batch of training samples. Okay? Stochastic means that you just take one sample at a time, compute the solution for gradient descent, and then take another sample and compute the solution again, and so on. Okay? So let's formulate this. So each time you take a pair x and Tn and use that to compute your criterion EW, right? Which is going to be now the sum of E sub n of W n1 to capital N. And each of these E sub n's are the error functions for each of these pairs, right? And therefore, hence, this criteria that we had here is going to be slightly different by just adding an E sub n where we only consider each of these simple or pairs at a time, right? So I'm going to have wk plus 1 is equal to wk minus, okay, some help here. Just that same equation, but now it's going to be eta times what? Anyone? E sub n, very good, right? Of my w, right? Same thing, or my wk if you prefer. Okay, so that's the idea of stochastic descent, stochastic gradient descent rather, and this is the idea of the batch. If you do everything using the original equation that I have already erased, that uses all the simples at the same time, right? Now there is an intermediate solution to that, which is called the mini batch. And as you can imagine, as you can guess, rather, the idea of the mini batch is that you take a compromise between using all the samples or just using one sample, and you take a subset of the samples, right? So take a subset. Let's call it capital X sub I, right? Which is a subset of my capital X that we've defined, right? And such that the union of all these subsets it's equal to the original set, right? So that I actually use them all. And there are many ways to define this. You can do subsets that are disjoint. You can use subsets that have repetitions. You can use etc. Right? So there are many ways to define these different algorithms. Okay? Any questions? So with that, now we come to the definition of the algorithm that the main algorithm that we're going to use to train these networks with this training set, capital X, with corresponding samples and targets when targets are given. Okay? And that's called the backpropagation algorithm. So let's get to this. Now, most people these days call this backprop, just because everyone wants to simplify or reduce the number of characters they need to type. Again, get that if you type backprop enough times, maybe you save, 5 minutes of your life at the end of your lifespan working on this. All right, but it's an easier word to pronounce as well. Okay. So we need the method to, so the reason for this is that we need a method to compute the weights of this first layer, this last layer rather, and then a method to compute the previous layer's weights, and then the previous if there are more, and so on, right? So we know how to do this because, remember, our error function is the least squares error function that compares the output of this network with the actual target value, right? So we know how to compute this error. And with this error, we know with this stochastic gradient descent or batch algorithm or mini batch how to actually change these weights. But now, how do I change these other weights here? And the idea is that I need to backpropagate that error that I have calculated here to compute what is the error in that middle layer. Okay? So we need two things. First, I need a feed-forward pass that is going to get me from the original x here to my, my f of x or y of x, right? And then I can compare this with t, and that's going to give me my error, right, squared, right? Okay. And then once I have done this, I need another method to now compute or backpropagate the error EW, right? So this is what I'm looking for. I need a method to backprop EW. Okay, make sense? All right, so let's see how I can do this. Now to simplify this, let's start with a linear model, and then we extend it to nonlinear, as we have done before. So we'll start with the model yk is equal to the sum of my w, ki's, xi's for every I. Okay? And that's a simple linear model where my offset is 0, right? So it's even simpler. Now, if I have this, then I have that my E sub n for stochastic gradient descent is going to be given by 1/2 of the sum over all k of, let's see, it's y nk, going to call it minus tnk square, right? And what do I need to do to compute stochastic gradient descent? I need to compute the gradient, right? Whoops. OK, I kind of forgot to add the gradient here, right? So I need to compute the partial derivatives to do that. So the gradient of my simple n given my weights wij. And we know that this is going to be equal to this 2 over 2 is 1, so that cancels out. Now you see why there was a 1/2 here, so that the derivative is actually easier to write down. So this is going to be then y nj minus t nj, right, times the derivative of the function y. Remember, y, it's a function, right, that depends on x. And it's going to be xi then, right? Because it's the derivative with ij, the weight ij. It's the edge between xi and my vector, my new node j. So this is x and I. OK. So I can do the same thing, but with more layers. So let's extend these to 2 layers. With 2 layers, I would have my AJs would be equal to the sum over all I of wij times xi, right? And zj would be equal to some nonlinear function of h aj. Okay? Yes? All right. So in that case, the partial derivative of en over wij is going to be equal to, well, let's think about this. This is the partial derivative of n, right? And now the first thing I need to do is compute the partial derivative of n with respect to a, right? Which is the first layer. So this is the partial derivative with respect to ak. And now here, ak partial derivative of aj, okay, which is the second layer. Okay? And what am I using here? The classical chain rule of calculus, right? We're not doing anything special, just using the chain rule. And in particular here, right, for this particular case, as we have written it in here for the system, let's see, the partial derivative of aj over wij is going to be equal to xi, and the partial derivative of en with wij is going to be equal to the partial derivative of en wij times xi, right? Yes? Okay. And third question? What's that?
He says like that aj should be wij in the chain rule system. The second part, the denominator.
This one?
No, chain rule.
This one?
Yeah. Should be wij.
Oh, w, when? Oh, yeah, you're right. Well, you're right if you only have, right. Yeah, you're right. Okay, yeah, okay. So let me do it here, okay? So I'm going to call this here some value, right? This partial derivative of en with respect to wij. I'm going to call it some delta j, okay? Some value, whatever that is, okay? So I can write it in a simplified form. And that leads us to the simplified notation, which is k of delta k times ak with respect to some wij, okay? And the reason here I'm using ak and aj now is to consider consecutive layers, okay, of aj's, right? Okay? So I can keep applying this to every single layer, one layer after another. So you can consider this, if you will, you can consider this, you can change this, actually, let's change this here. We can change these to zi, right? So that becomes, instead of xi, the previous hidden layer, right? And if it's the final layer, meaning the input layer, it's xi, right? Yes? Yes?
When you define delta j, in that equation, you wrote partial derivative of en with respect to w is equal to partial derivative of en with respect to w times xi.
Oh my gosh, yeah, you're absolutely right. This is with respect to, right, so, yeah, you're right. Where am I? Okay, I don't know what I missed my note somewhere. So this is, you're absolutely right. This is, okay, let's think about this. So where did I go wrong? This is the partial derivative with respect to ak, right? Am I right? It's ak, isn't it? Oh, or, no, it's ak, right?
No, he means in the above.
This one? Yeah, what's that? Okay, one at a time. Okay, you go. Yeah, you go.
I mean, the second part should be partial derivative of w at j.
This one.
Yeah, is a chain rule.
wij, okay. So you want to have here wij. Okay? Right? Okay. Or someone else?
I was just thinking, I don't have anything.
Okay, good. So now let me go back to where I was. I have my partial derivative of En with regard to, so this is the correct one, so to wij, right? And this is the partial derivative of En with respect to ak, right? Am I right now? Is that better? Okay. And sometimes it's better just to think about it than just looking at the notes, right? It's just straightforward. Okay, so if I do that, then this is equal to what? This is the nonlinear function h, and I have to take the derivative of that nonlinear function, right? If I use the logistic sigmoidal, I take the derivative of the logistic sigmoidal, right? So I'm just going to put this as a derivative of whatever nonlinear function that I'm using here times the sum of wkj's my delta k's, okay, over all k. All right, excellent. So in essence, what we're doing here, actually let me do that probably. What we're doing here, if I have these nodes here where I have compute delta k and delta j, right? And remember obviously that let's call this delta j and this zi. And then remember that there will be w between k and j, right? And this would be between j and, actually let me call this I for different, between j and I, and so on, right? And now what I'm doing with gradient descent is I'm projecting these values backwards by using this equation with that I have obtained with the chain rule, right? And then to here, okay? Yeah? Is there a question? Okay, good. All right, so let's summarize the algorithm in some more formalistic, in a more simplified formalistic way. So error backpropagation algorithm. Whoops. And this is actually pretty much straightforward from everything that we have, but let's write it down so you can experiment with it tonight, right? You can go to MATLAB and implement this in a few minutes. So you see how it works. And I do recommend that you do that. Now, of course, you can just go to MATLAB and use its already implemented method, right? But I strongly recommend that you practice with this, right? Because it's important you know how this works. So using our xn, right? Remember, if we're doing a mini batch, this is a subset. If we're doing batch, this is the whole set. And if we're doing a stochastic, then this is just one sample, right? And here it's going to be 1 through n, or actually capital N. Compute, so with this, using this, we compute the output of the network. And in our example here that we have given, right, this is aj, it's equal to the sum over all I of w, ji's and zi's. I'm going to write it maybe for layer layer small l, display the layer, and then the zj at layer l plus 1 is going to be haj, right? And in general, you'd write more generally. You can just write that you're applying the function fi for, or fl, let's call it for the lth layer, right? Whatever function that I'm having here from the input vectors of the previous layer to the output vectors of the other layer, right? Okay. So that's the forward path that we've discussed. So given my x or set of x, I obtain my y or set of y's. Yes? Okay. Now with that, we can compute my delta k. And what's delta k in the last layer? This is the difference between the output and the expected value, right? So my yk minus tk. And now, after I have done this, that's a result, that's the deltas that I have here, right, for that layer. And now I have to backprop to calculate the other deltas for previous layers, right? And to do that, I use backpropagation. So I'm going to say that my delta j is equal to h prime, the derivative of h of aj, times the sum over all k of wkj delta k, right? Which is the equation we've derived here. And we're almost done. Once I have these deltas, now I can compute the derivative of the error function. Now, if I'm using linear least square, the least squares error function, that's my error function. Once we move on with more complex modern methods, we're going to use different criteria, okay, in here. But for this, we're going to use the partial derivative of E sub n with respect to the weights, ij's, and that's going to be delta j zi, right? Yes. Or this is with a stochastic gradient descent, or if using a mini batch or the batch algorithm, then I'm going to have the sum over E sub m of wji equals the sum of all the E sub n's with respect to these wji's, right? Right? Obviously, right? And then again, you know, subject to, as we did before, that the sum of all the xm's that we're using is equal to the total set of Turing simples that we have. Okay? How are we doing? Good? Okay. So this is just a way to solve nonlinear least squares, right? We start with the least square solution, but our function is nonlinear, which means that our error function is not going to be convex, because if the original function f of x equals y is linear, right, that is going to lead us to a least squares error function that is convex because it's the square laws, right, or the norm 2 that gives us this error function, which is z squared, let's say. It looks something like this, right? It's the classical square function, right? and that's convex, which means that we can find the minimum because there is a single minimum, right? But when we have a nonlinear function, we have that other result that apparently I erased that may look something like this, that has multiple minima, right? And we have to find at least one, okay? Doesn't matter if I'm going to find this or this, but I have to find one, which means that I have to start at some point, at some random point, so initialize W with some random numbers. And then, although there are methods to initialize things, and that's important, and we'll get to all of this. And then once I have this initialized, say here, I can find that minimum. And if I initialize here, instead, I find this other minimum, right? Okay. All right. So let's see a simple example. That's me. I forgot to turn that off. All right. So let's see a simple example so that we can practice this, because if you want to work in computer vision, you're going to have to derive these things all the time. And we're going to be doing this first for low-level vision. That's why we're introducing it now. Then in some mid-level vision, and then certainly in high-level vision, we're going to extend this and complicate it much more. OK. So an example. Very simple example, OK? I'm going to do a very simple one. So I'm going to use the same model that we have been using until now. And I'm going to change the nonlinear function from the logistic sigmoidal that I used to a 10H, OK? So let my nonlinear function h be the 10H of A, which you may also write as EA minus E negative A. Yep, and EA plus E negative A. OK. And let, as before, my AJs be equal to the sum of my WJIs. I'm going to start at the first layer, layer 1, times xi. And remember, this is I from 0 to capital D, I believe we said. And Zj is going to be now h of AJ, which is the 10H of AJ. And finally, yk, it's equal to the sum of wkj's of the second layer times Cj, right, for j from 0 to m. Okay. So if this is our model, right, so this is our model, or our neural network, if you prefer, then to find a solution, we compute the deltas, right? So my delta k is equal to yk minus tk. My h prime of A is equal to 1 minus ha square. And my delta j is going to be equal to 1 minus zj square times the sum of wkj delta k for all k. So let's say from 1 to capital K. Right? So that's a small k, that's capital K. Okay? And the partial derivative are going to be given by, let's see, the error function of n with respect to the parameters. So let's say 1 again, right? It's going to be delta j times xi. And the partial derivative of n with respect to the parameters in the second layer, it's going to be the same thing. Now it's going to be delta j times zi, right, instead, because that's the second layer. Okay, now as you may know, this is just a very rudimentary way of representing the partial derivative, right? Because usually we are not going to have such simple models, and we're not going to have such simple input and output vectors, right? So let's think about what we can do, or what we can have, rather. We can have as input, in the simplest case, we could have just a constant, right, as input. X can be just a, say, real number, okay? We could also have a vector, right? X can be a real number of p dimensions, right, or p. But we could also have a tensor, right? We could have an image, right, which is a matrix. We could have a multiple images in a video sequence, right, which is via tensor, etc., right? So we have any type of tensor. And again, if you don't remember from 5460 because you took it long ago, please do review those lectures in 5460 that cover tensors, okay? Hilbert spaces and tensors, which are the same ones that I ask you to review at the beginning of low-level vision when we talk about linear filters, right? But it's important that we understand tensors because we're going to use them constantly here. Okay, so usually what we're going to do then instead is to represent these things. So let's see, where am I? To represent this with the Jacobian, right? With the Jacobian matrix. There's another one which is a generalized Jacobian that I'm going to get to, hopefully, maybe today, if not next time, okay? Which is for tensors. But let's start with the Jacobian matrix that you already know. So let's review it very quickly. Now recall that what we have is we start with x. We use some function f to project this to my intermediate or hidden layers z values, the z vector. And then I have an output vector y that's given by some other mapping function g, right? And we have written this before as y, it's equal to g composed with f of x, right? And as we know, the chain rule is that if I want to compute the partial derivative of y with respect to x, this is going to be the partial derivative of y with respect to z first, right? And the partial derivative of z with respect to x. Yes? Make sense? Excellent. Now, obviously, that's trivial if we're talking about scalars, right? So if I have a scalar variables, that is trivial. But how about if I have vectors? So let's consider, let's assume that f, it's a mapping function from this first f here, from some space of n dimensions or d dimensions to R, to 1, okay? So I'm going from a vector to a scalar, right? So if I have this, then the new vector, let's call it z plus, right? The new vector of values for z is going to be given by z plus the partial derivative of z with respect to x, right? Just this part right here, times the increment of x, correct? Okay? Well, remember here, I'm considering with z plus, it's equal to z plus, whoops, it's equal to z plus that increment that we have considered, right, of z, or x plus equals x plus the increment of x, right? Same thing as we've done before. Or you can consider also k plus 1 and k here, right? K plus 1, k. And here, right, where the partial derivative of z with respect to x, it's equal to the partial derivative of z with respect to x1, because x has n dimensions, right? And so on up to x capital N, right? Do you say capital N? Yeah. Right? So this is in the case of scalars. This is in the case that I map from n dimensions to 1 dimension. And then the final case, right? Well, not the final, but almost, is that if I have a mapping between n dimensions and m dimensions, right? From vector to vector. And then in that case, to compute the partial derivative, I use what's called as the Jacobian matrix. Let's call it capital J, which corresponds, it's the same as the partial derivative of z with respect to x, which is equal to, let's see, the partial derivative of z1, like here, with respect to x1, all the way to the partial derivative of z1 with respect to x capital N, and then z2x1, z2xn, and so on, all the way to the partial derivative of zm with respect to x1 and zm with respect to xn, right? And that you know, because I know you have seen that before, this is the Jacobian matrix, right? Okay, so far so good? Excellent. Now, let's generalize this even further so that we can have not only scalars, not only vectors as inputs and outputs, and hidden layers, but any tensor, okay, of any rank. And remember, 0 rank would be scalars, rank 1 would be vectors, rank 2 would be matrices, right, and so on. So you keep adding dimensions to the tensor. So in the more general case, we're going to write that we have a functional mapping F that goes from the real domain of, say, n1 times n d sub x, probably, for the input variable x. And I map this to the real domain of m1 times m d sub, is that z? Z, yes. Okay. So now I have n dimensions in the first order, and 2 dimensions in the second, and 3 in the third, and so on, right? Yep. And now here, the partial derivative of z with respect to x is called the generalized Jacobian. And whose shape, let's say that, whose shape is m1 times m2, m3, dot, 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 m dx, actually dz, because these are the m's, times n1 times m2 times all the way to n dx, right? Right? And it's the same thing than the Jacobian. The Jacobian, what did we have? We had an input vector x of n dimensions, right? And an output vector of m dimensions. So what's the output? It's a tensor of an additional rank with n dimensions in that dimension, right? And or in that direction, rather, and m dimensions in that other direction, right? Yes? And that's the same if you start with tensors and you have n1, n2, n3, n4. And the other tensor is m1, m2, n3, m4, m5, m6, right? What do you end with? Well, you end up with all these m1, m2, m3, m4, m5, m6 times n1, n2, n3, n4, right? And that's called the generalized Jacobian matrix. Excuse me, the Jacobian period, or tensor, if you want. Okay, so we're typically going to write this to make it more palatable for implementing these things in MATLAB or Python, if you prefer to use Python. So turns out, just saw these online today in the IEEE magazine, that the most popular languages right now are Python, I think was number 1, followed very closely by C, C++, and MATLAB was like 5th or 6th in the list, which is not too bad still for, I mean, it's expensive software. So, I mean, you know, here you have it for free, but if you go to work for a company, it's a very expensive software to have, whereas Python, you know. So, but Python is becoming a really popular method, computer language to use. So it makes sense to learn it. Okay, so we're going to typically, we will typically write this as this, I mean the generalized Jacobian tensor, right? As a partial derivative of z with respect to x. And when I want to refer, remember from 5460 when we talk about tensors, when I refer to specific locations of this, I'm just going to indicate this here, I and j, right? Which dimensions I'm interested in. So, for example, if I have ij here, what this is going to mean is going to mean the partial derivative of zi with respect to xj. Okay? Right? Okay. And now here we can write that this I, it's some integer value, right? In dz, is that I, yeah, in dz, and j is some integer value in dx. Okay? So with that notation, we can write that the partial derivative of z with respect to x times that increment of x that we're interested in adding, right? That this is going to be equal to the sum of my z x I j and the increment of x in my I, because remember I, it's the direction in which I want to increment this, right? And because I'm going to sum over all I here, I could write this as in more computer language format, I guess. Zx, let's say j, comma, dot, dot, to indicate all the column, the whole column of that tensor, right? Times the increment of x, right? The column or the row, depending on what it corresponds. And I should say row or column in quotation marks, because there's, you know what I mean, right? Is that it's like a row or a column, but we're talking about a tensor. So that's the concept of rows and columns are a little bizarre here. Okay? Okay. And then if we use the chain rule, then what do we get? We have that the partial derivative with respect to of I with respect to x, rather, for the locations ij are going to be the sum over all k of the partial derivative of y with respect to z of ik times the partial derivative of z with respect to x of kj, right? Am I right? Right? Make sense? So I'm going to consider all the k's, right, that connect me from the i's to the j's of y and x, right? And this is equal to the partial derivative of y with respect to z. And I'm going to use this notation here that we like in programming to indicate the row or column, right? This row for that tensor, and times the z of this column. Okay? And there it is. The ith row and the jth column of that tensor, right? Okay? All right, so let's see how we can define backpropagation with tensors now. And this is going to be our true algorithm, right? The final generalized version of the algorithm that we're mostly going to work with. So remember that every layer of a deep neural network in general, and especially of a deep neural network, it has many, many hidden layers, right? Is nothing else than a functional mapping that we have defined as y is equal to f of x given my weight vectors, my parameters for that layer w. And in general, we have to indicate that these three elements are going to be tensors. Okay? If they are scalars, they are tensor of rank 0. If they are vectors, rank 1, and so on, right? Dot order 1, right? If their matrices order 2, and so on. Okay? So what's the next thing? We then define a criterion that we want to either minimize or maximize, like the least squares criterion that we have defined. And we want to use gradient descent or ascent to find that minimum or that maximum, okay? According to that criterion that we have defined. Now, this criterion in machine learning, when you build classifiers and when you build regressors, classifier in machine learning means that you are given an input x, the output y, it's an integer, right? 0, 1, 2, 3, so that you're actually classifying things into boxes, right? The 0 box could be in speech analysis, could be words, and in computer vision, it could be objects, right? So tables, cars, people, and so on, right? And regression means that both x and y are continuous variables, okay? Now, in machine learning, when we talk about this criterion, this is called the loss function. Okay? So that when you read this in the literature, you understand what that means. It's referring to the exact same thing that we're doing here. Okay. Thus, we wish to compute. So, okay, I didn't write this. So we have this loss function, or our criterion, if you prefer, L. Okay. So we wish to compute the partial derivative of the criterion with respect to x, which is going to be the partial derivative of our criterion with respect to y times the partial derivative of y with respect to x. Right? And we also want to compute the partial derivative with respect to w, which is equal to the partial derivative of L with respect to y, and the partial derivative of y with respect to w. Okay? Now, so that's our solution. And we are basically done. This is the solution, and we already know how to do that, right? But there is a problem. In practice, these generalized Jacobians are just enormous, right? So these typically are going to be, not always, but typically, they're going to be too large for us, okay? And we have to find a way to define a solution. So I want to derive a method to solve this. And to do that, I'm going to give you a first set of notes, and then I'll leave the rest for a homework, right? So that you go home and you actually practice these things, because they are extremely important for everything that you're going to do in computer vision. So I really want you to practice this. So let this function be x w, meaning that this is a simple linear function to begin with. And then we'll generalize it, OK? And here y is going to be given by y11, y12, y13, again equal to xw. And I could write x as x11, x12, and w as w11, w12, w13. I'm just simplifying everything, right? So that we can compute very nicely. And what's this equal to? This is equal to, let's see, x11, w11, right? Plus x12, w21, and then x11, w12, plus x12, w22, and finally x11 times w13 plus x12, w23. Right? And now let the partial derivative of L with respect to y be delta, let's call it y11, delta y12, delta 13. Okay? So with this setup, I want you to tell me in a homework, how can you now compute the partial derivative? How to now derive the partial derivative of L with respect to x. Okay? I'll put that in Carmen as well. Okay? Think about it, and we'll discuss the solution next time. All right? Have a great weekend. Enjoy the homework.